So ecosystems, even though we've had it before, here it is again, includes all biotic and abiotic factors within a specific area. The size of ecosystems varies. Dynamics determined by energy flow and chemical cycling. So a lot of this chapter is going to be on the energy flow and the chemical cycle. Now, a lot of the earlier chapters dealing with, dealing with ecology. I keep calling it science light. The terminology is not too heavy. The concepts aren't too difficult. A lot of this stuff you're familiar with, you've already had before. But there are some theories now that we're going to be touching upon. Okay? We hit on a few, we're going to hit on a few more. So you need to be aware of the theories, the ideas that come out in ecology. So ecosystems includes all biotic and abiotic factors within a specific area. First up, the law of conservation of energy. Energy can either be created or destroyed, only transformed. That's one of the basic concepts. We talk about it in Bio 4. The non-majors get this. Energy can either be created or destroyed, only transformed. I go to the wall, I flip a light switch. The electricity goes through the wires to the light. When it gets to the light, it causes the electricity to be converted into light and heat. No longer electricity. It's not like you flip a switch and bolts of lightning come out of light. It's transferred into another form of energy. And if I have all the heat given off, and if I add up all the light given off, all that energy, then I can probably account for all the energy going through the wires to cause the light to shine. Energy theory is an ecosystem, that's solar radiation. All energy, all ecosystems begins with sunlight. Energy is transferred within an ecosystem from plants to herbivores to carnivores. We can't sit out in the sun and gain all this energy that we need just by lying in the sun. In fact, by laying in the sun, you tend to burn more energy. It makes you hungry. You get in the pool, play around a little bit, it makes you hungry. No matter how much carbon dioxide you suck in, how much water you drink, you don't get the energy you need. You can't convert sunlight. You need to do that with plants. And so we get our energy either directly from plants or from organisms that eat plants. Energy is lost as heat and reflection. More on that. Second law of thermodynamics. Energy transfers, transformation are not completely efficient. Some energy will be lost as heat. You see this guy, bison, buffalo, call it whatever you want. We call them bison because most places in the world, when you talk about buffalo, you're talking about water buffalo. They're more widespread. So, whatever you want to call that. You see, it's cold, he's breathing out, he's losing a lot of heat as, a lot of energy is heat there. It's coming out of his breath. Okay? We're mammals. We're not entirely efficient at converting everything we eat into energy. Much of it is lost as heat, but that's okay. We're warm-blooded. We have high metabolic rates. We're going to lose energy as heat, and that warmth helps keep our metabolism high. Energy flow through an ecosystem is ultimately lost as heat, but is constantly renewed by the sun. As long as the sun keeps shining, it doesn't matter how much heat or how much energy we lose, we keep getting more of it every day. So each ecosystem is continually replenished by sunlight every day at sunrise. We've touched on this before, I'm not going to hit it too hard again. Energy flow and trophic structure, I changed it up a little bit. Since we're talking about consumers, I dropped the plants and I added a snake. Primary consumers, heterotrophs feeding directly on plants, we call these herbivores. Secondary consumers, heterotrophs feeding directly on herbivores, these are the first carnivores. And then tertiary consumers, heterotrophs feeding on other carnivores, secondary carnivores. So in this little food chain, I've got the rabbit, I've got the snake feeding on the rabbit, and I've got the coyote feeding on the snake. Okay? So energy flow goes from the plants into the rabbit, the plant into the snake, and the snake into the coyote. And again, this is a little bit of reiteration of what we've talked about before. Yeah.
Omnivore, like the humans, would be a third degree because
We feed on both plants and animals. Yes. Yes. If you're a vegetarian, you'd be second, but if you're an omnivore, yes, you'd be third. Or tertiary. I like that word. Quaternary. I don't like that word either. It's hard to pronounce. Anyway, I digress. So, we've talked about this stuff before, but we're tweaking it a little bit. I mean, literally, chapter 56, I came across some things, word for word, that we mentioned before. It's like, why talk about this again? I know I put it in this because it was in the chapter. I don't like redundancy, so it was fine. But sometimes I'll leave stuff in there because it's focusing a little bit from a different perspective than what we've talked about. Detritivores, heterotrophs that obtain energy from dead, decaying organic material, which is known as detritus, which is why we call them detritivores. We've just relabeled something we've already talked about. Decomposers is what their common name is. We talked about them as being saprophytes. We talked about them as bacteria, as protists, as fungi, and here we are back to the fungi. Recycle nutrients back to producers. So heterotrophs that obtain energy from dead decaying organic material known as detritus and recycle nutrients back to producers. Ultimately, everything dies. And in nature, there is no waste. So what nature does with these detritivores is start breaking down the dead or decaying organic material. So there's still a lot of good stuff in that. There's still a lot of good nutrients that we need to recycle back into the living organisms. And so that's what they do. So it's trying to recapture energy and recycle it, so it's just not lost. Obviously, it's in italics, so I'll write it down. Earth is bombarded with enough daily solar radiation to supply energy demands for the entire population, human population, for 25 years. And you're sitting there thinking, oh my goodness, does that mean 25 years the sun's going to go out? No, read it carefully. You guys don't read carefully. Enough daily solar radiation. As much sun as we get in one day is enough to supply us for 25 years. Okay? When solar radiation is absorbed, scattered, or reflected by the atmosphere, or what energy reaches plants, 170 billion tons of organic material is produced annually. So we've got sunlight coming down. Some of it actually reaches the planet and is absorbed. Some of it might be lost to heat back out into space. Clouds, the atmosphere might reflect some of the sunlight off. In some cases that's good, others maybe not so good. We'll even talk later again about how sometimes the clouds, the atmosphere, full of carbon dioxide and water vapor, bounce it right back down to Earth. Okay, primary production. We've got gross and net primary production. There is a difference between them. It's like your paycheck. What's your gross pay? What's your net pay? Gross primary production is total amount of light energy converted into chemical energy by the producers during a given amount of time. This is everything. This is your paycheck before everybody starts taking their little bit out. For the government, Social Security, all that stuff comes out. And then you're thinking, really? That's all I get to take home? Yeah. Organisms that carry out gross primary production, we're talking about prokaryotes, algae, and green plants. So gross is that line that looks really good on your paycheck. Yes. You keep going down and down, and so does your paycheck. Total amount of light energy converted to chemical energy by producers during a given amount of time. So this is total energy. It's all the energy producers convert. Net primary production, gross primary production minus the energy used by producers during respiration. Okay, I'm going to give you all this money in your salary, but you got to give me some of it back. So I need to put it away for your retirement, for your health care, or something like that. Well, that's what's going on here. Gross primary production is all the energy plants make, but they don't let us have all that energy. They need to keep some back. Because plants like us need it. Anything that grows, repairs, reproduces, and last time I checked, this does include plants, they need energy to do that. And so they'll keep a little bit of that energy back for them. So whatever's left over, that's what's available to herbivores. Net primary production is determined by the size of area covered by primary producers. Are we talking about something like a tropical rainforest where there's a lot of primary producers carrying a lot of gross and net primary production? We're talking about something like a desert that might have a large area but not so many primary producers. Not a lot of primary production going on. Also, the efficiency of primary producers. Some plants are more efficient at converting sunlight into energy than others. So, gross primary production, the total amount of energy. Net primary production is that energy minus whatever the plants held back in order for their own personal use. And again, determined by size of area covered by primary producers and the efficiency of primary producers. Okay, something we don't always think about primary production in aquatic systems. Usually when we talk about plants, we're talking about terrestrial plants. There's algae too. And in fact, the oceans are teeming with so much algae that there are huge carbon dioxide sinks, which is good. They take a lot of the carbon dioxide out of the algae. 50% solar radiation is absorbed in the first meter of water. Half of it. Another 5% more solar radiation is absorbed down to 20 meters. I think in some of the images we looked at for the stratification of marine freshwater biomes, the photic zone went down, what, about 100, 200 meters? But I mean, you're getting down to very small increments of light beyond 20 meters. Solar radiation increases from the poles to the equator where the greatest amount of light hits the Earth. And we've touched on that before too. Again, don't try and learn everything word for word. Understand concepts, draw connections, connect the dots. When we talked about the amount of light hitting the Earth, we talked about how it hits the equator most and the poles least. And then we talked about gradients between tropical and polar environments. And a lot of that has to do with the amount of sunlight that hits those areas. So look for threads, look for streams, connect these things. Make it easier for you to understand instead of isolating these and trying to learn them independently. Nutrient limitation. Element that must be added in order for primary production to increase in a particular area. We're going to talk more about this today. Marine limiting nutrients include things like phosphorus, nitrogen, and iron. Element that must be added in order for primary production to increase in a particular area. When we try and fix this on land, what are we using basically to help the plants out?
Fertilizer.
Fertilizer. Trying to figure out the nutrients that limit them so we can add it to them so they can grow better. Bigger, healthier, more fruit, vegetables, whatever. Now it's different for terrestrial environments. Phosphorus and nitrogen are pretty common in both nutrient limits for terrestrial and aquatic systems. Iron, you don't hear so much about a need for it in terrestrial systems. Potassium is usually a greater need. You don't have to write this down. Something to think about, rest of your wrist a little bit, fingers, whatever. Okay, nutrient limitation. What we can do, and they have tried this before. Ship offloads iron. Iron causes growth of phytoplankton, which capture carbon dioxide. Okay, that's good because it becomes a CO2 sink. We take more carbon dioxide out of the atmosphere, we reduce the effects of global warming or climate change, right? Everything sounds good. Dead plankton. Well, plankton doesn't live forever. Eventually it's going to die and sink. When it sinks to the bottom, what happens is it'll lock the carbon down into these deeper, colder layers. Okay, so what's the problem? Fantasy, plankton populations rebound to historic levels. If the plankton comes back, the fish come back, so revive fisheries and sequestering vast amounts of carbon. It's a win-win-win situation. Here's the problem. Iron leads to the depletion of deep water oxygen because now you've got all this going on down here where the dead plankton sink. The organisms, the tridivores that break this down are going to be consuming oxygen. Alters the food chain and promotes toxin species. Carbon dioxide soon resurfaces. Basically, we need to have a much bigger knowledge of what goes on in nature before we start to try to fix things, try to make adjustments and things, because usually our adjustments don't work out so well. We'll talk more about that as well. Upwellings. When nutrient-rich water circulates to the ocean surface from the ocean floor, results in higher primary production. Well, what did we talk about before? This sounds real similar to this. In the lake? What is it? No. That happens in fish. Turnover. Yeah, turnover. Usually happens in the spring or the fall when the water temperature starts to change and the colder water getting more dense falls to the bottom, pushing those nutrients up, taking the oxygen down with it, creating a more nutrient-rich lake top to bottom. So we're seeing basically the same thing here. This is more common in oceans though. When nutrient-rich waters circulate to the ocean surface from the ocean floor. So what happens? Kind of like Southern California here. Wind blows parallel to the coast. Warm surface layer blown offshore. Cool water comes up from below, so we've got the wind blowing. The warm water comes out. The cold water circulates, and this is what brings everything up from the bottom. Now it's not like you go swimming in just a mouthful of seaweed or what used to be seaweed. It's not like that. You probably don't see most of these nutrients. But the organisms living around these areas do, and they do benefit from these upwellings. Eutrophication. We'll mention this again. We're not going to dwell on this much as we will now. Eutrophication process in which nutrients, mainly phosphorus and nitrogen, become highly concentrated in a body of water, resulting in increased algal growth. I'm not sure if the frog's happy there or not. He blends in pretty nicely, but he's got to be thinking, where's the water? Results in excessive primary production. Caused mainly by human sources like sewage, agriculture, and landscaping. Okay, agriculture and landscaping, what we're doing is we're fertilizing our plants. We want them to grow, to produce more fruits and vegetables. We want plants in and around our homes to look nice. It rains, it takes those fertilizers and washes them directly or indirectly into a water source. Now, what we use to fertilize the land plants can also be used to fertilize some aquatic plants. And so the same effect. What grows on land is now going to grow in the water. So you get all this plant growth in the water. You get actually too much plant growth going on in the water. We'll talk about the effects of that in a second. Sewage. Have you ever been to a nursery, Lowe's, Home Depot, and found bags of manure that you can actually take and use as fertilizer? You can't. I mean, some people swear by it. If you've got dogs, I would recommend it because they love to roll them. Dogs are funny that way. They think it's like perfume. And of course, it's an outside dog, no big deal, just take the hose to it. An inside dog, well, you might be washing your sheets. So sewage, human sewage would have the same effect. It's going to act as a fertilizer and cause a lot of plant growth in areas where it's not accustomed. So eutrophication, process in which nutrients become highly concentrated in a body of water, resulting in increased algal growth. increased growth of algae. Here's how it works. Nutrients load up. Excessive nutrients are fertilizers that flush from land and rivers or lakes by rainwater. Let's say Farmer Brown's up here, he just fertilized all his crops. A big rain came along as soon as he put the fertilizer down. And it washed all the fertilizer down to the small pond that he had. Plants flourish. These pollutants cause aquatic plant growth of algae, duckweed, and other plants. Anybody ever seen duckweed, Linda? It's the smallest flowering plant in the world. If you have aquariums, be careful. You don't want it in there. It might look pretty on the top and everything, but filters do not like it. 3, algae blooms. Oxygen is depleted. Algae blooms, preventing sunlight reaching other plants. Plants die and oxygen in the water is depleted. Decomposition further depletes oxygen. Dead plants are broken down by bacteria. Decomposers using up even more oxygen in the water. And eventually what happens, the death of the ecosystem, oxygen levels reach a point where no life is possible. Fish and other organisms die. So overall, it's a bad thing. The other thing that you get is all this plant growth keeps falling down and falling down and falling down. Eventually, it fills this in. So what might have been a nice little pond on your farm one year is now wetlands the next year. And then after that, it may be a swamp, and after that, maybe nothing. Yes?
Is that what happened over at the Salton Sea?
I don't think that's the problem.
Too much salt there?
They did have a lot of stuff washed into it, and it has been a chronic problem since then. I'm not sure what the Salton Sea's source of salt was. Wow, nice alliteration there. But yeah, it is very high salt content. But I don't think that's what causes all this stuff. I think it is probably stuff from agriculture in and around the area that washes in there. Okay, primary production in terrestrial systems. We'll do a few more, then we'll take a break. Temperature and moisture are 2 key factors in terrestrial primary production. Highest primary production is in the tropical rainforest, lowest in the tundra and desert. So what does that tell you about temperature and moisture, just those 2 key factors? How do they play into this? Describe it. I gave you a couple of examples there.
The more moisture and temperature, the higher production.
Exactly. The more moisture, the higher temperature, the more primary production. Now, moisture could be rainfall, it could be humidity, whatever the case might be. You have higher primary production. In the tundra and the desert, where you have very little moisture, temperatures all over the place. For the desert, tundra, you have very little of both. Lowest primary production. So, you guys know what tropical rainforests are. You know they're hot, they're humid. By virtue of their name, they get lots of rain. Again, connect the dots. Highest primary production in places that are the warmest and have the most moisture. Okay.
Does that mean that less energy is lost in, like, as you travel through the levels of the biospheres in the tundra and the desert because there's less energy overall?
You could look at that that way. You probably want to say that less energy is generated, but that's because the organisms become adapted to the fact that they can live on very little energy. You just don't have the great variety of species there that can do it.
Is it still 90%, 90%?
Yes, that will always be the percentage. You always lose 90% from one trophic level to the next. That's just the standard. Actual evapotranspiration. That's a quadruple word score in Scrabble. Evapotranspiration. Annual amount of water transpired by plants and evaporated from landscapes. I'll show you a diagram in a second as to what we're talking about. Basically, any water that's at the surface of the earth and that goes back into the atmosphere, whether it's evaporating directly from the earth, or whether it makes its way into the roots of plants, up the xylem, out the leaves and into the atmosphere, that's evapotranspiration. Evapotranspiration increases with more precipitation and solar radiation. Again, it makes sense. More precipitation, the more moisture you have in the area, the more evapotranspiration. You guys don't really experience this out here very much, but I remember back east in the summer, you get a rainstorm. If it's hot enough out, you just see the steam rising up off the pavement from that rain and hitting that hot pavement. So you get enough moisture that you actually get steam. Out here, it rains in the summertime and pretty much evaporates before it even hits the ground. So the solar radiation warming everything up and causing the moisture that falls to evaporate. So more solar radiation, more photosynthesis, more evapotranspiration to the trees. Again, keep drawing connections here. Make it make sense to you. Real general diagram of what it looks like. We get rainfall, it's the surface, sometimes it runs off. It can evaporate from water. It can evaporate from land. It can evapotranspirate. I'm not sure if it's a word or not, but I'm using it from the plants. And here's another chart showing what we've been talking about, natural evapotranspiration versus net primary production. The highest in both categories, tropical rainforest, lowest desert, and then the Arctic tundra down here. So that kind of illustrates what we were talking about. Secondary production, amount of chemical energy converted into biomass by heterotrophs during a given amount of time. So primary production is what plants give us. Okay? Secondary production is kind of what we take from the plants. Amount of chemical energy converted into biomass by heterotrophs during a given amount of time. So the plants take the sunlight, they convert it into energy, that's primary production. The organisms, the heterotrophs that eat the plants, take that energy and convert it into energy within their bodies. So that's secondary production. Herbivores eating plants. Got an example of the browser and the grazer here. Browser in the trees, grazer on the grass. Yes, let's do one more little thing. Trophic efficiency. We already talked about trophic being feeding levels, right, or feeding structures. Troph, autotroph, self-feeder, heterotroph, other feeders. A troph means to feed, so trophic efficiency. How efficiency, energy is moving through trophic levels. Amount of energy transferred from one trophic level to the next. Marley brought this up already. We've talked about this before. It's my way of reiterating, reviewing, reminding you of this. 10% energy is transferred between levels, 90% energy is lost between levels. So I get 10,000 kilocalories of energy starting in the producers, and they get all theirs from the sun. The primary consumers can only convert that 10,000 kilocalories into 1,000 kilocalories. So they only convert 10% of that, 90% is lost. The secondary consumers can only eat about 100 kilocalories worth of energy from the primary consumers. And then the tertiary consumers, the third degree consumers, only eat about 10 calories to 100 calories from the secondary consumers. So we see from one trophic level to the next, 90% energy is lost, only 10% moves from one trophic level to the next. And remember that 10% energy also reflects 10% of the numbers. So I only have X amount of energy to support X number of organisms, and also biomass. If I only have X number of organisms, I dehydrate and weigh that, I'm only going to have X amount of biomass. So there's a direct correlation between energy, numbers, and biomass. Mark.
Where's it go?
What?
The lost energy? Is it heat?
Most of it's heat, waste, biochemical reactions. I mean, a lot of it's just being lost to waste.
And then recycle.
And then recycle. Absolutely. Questions?
My question was kind of like hers. So it pretty much that 90% goes to like run the body of the animal or the species.
Either is going to be lost in the metabolic processes, or if it's something, especially more warm-blooded organisms can be lost as heat.
Okay.
But I mean, you're going to generate a little bit of heat in metabolic processes every time you eat. You're going to elevate your body temperature, at least here where you're digesting food.
So those bugs and insects that feed on plants, they're generally, they have a lot of energy. They should have a lot more energy than something like a snake. So they're like bursting with energy.
You really can't draw a correlation like that with it because they are technically ectotherms, poikilotherm. So by definition, they're going to have a relatively low metabolic rate. But to get that energy out and to remain metabolically active, then yes, they need more energy to do it.
So like, it's just weird how something that small has 1,000.
Well, there's lots of them. We're just talking about 1,000 kilocalories of energy, not per individual insect, but for all the insects feeding on all those plants.
It's because they reduce in numbers, is it?
Yes, because they can only support X number of plants.
But
So
still,
for us.
proportionally, there's still a lot more energy. Of course,
There's just a lot more.
That goes back to what you were saying about the how the bigger the animal, the needs you need more smaller
Granted,
animals.
burn more energy, but overall, now that's compensated by the fact that you have lots of insects in a given area versus insect eaters.
Don't humans mess that up?
Oh yeah, that's everything. You can turn this upside down and say you have one tree. Just look at the biomass of that one tree. Look at how many organisms are going to be living on that tree. So you kind of turn the pyramid upside down, depending on the size of the organisms of the trees. James?
These primary, secondary, and tertiary consumers are they interchangeable? Like with like the species? Because like can't bugs like eat animals and like then
Usually not actively. Maybe if an animal does. Go ahead. It's a little bit low. 76, 78. Okay, the green wolf hypothesis. Predators hold terrestrial herbivores in check, preventing them from consuming excessive amounts of plant biomass. We're talking about carnivores, parasites, diseases, any of this. Whatever keeps these guys in check from. A little redundant there. Carnivores, parasites, diseases, whatever keeps them in check from eating too much green stuff. Because of that, herbivores consume less than 70% of total plant biomass, so just a little bit of it. And of course, if we keep eating herbivores, especially things like beef, then we're going to have to allow them to eat some of the plant biomass. So the green wolf hypothesis, I'm guessing just about everybody's got this one.
Starting.
Okay, keeping herbivores in check. Intra-specific competition within species. There's only so much plant biomass to go around in a given area, so you're only going to have so many herbivores that can eat it. Those that are better suited to the environment will succeed and eat more, the others will eat less. It's into the competitive exclusion principle, look that up. Interspecific interactions between species. You're going to have different herbivores maybe competing for the same source at the same time, trying to defend themselves against predators, interspecific interactions. Abiotic factors like climate. If you get a really dry season and it hits, wipes out all the plant biomass, it's going to wipe out a lot of the herbivores. Nutrient limitations, especially in some place like a desert ecosystem where the nutrients are relatively limited, then it's going to limit the plant growth. And then plant defenses. We talked about this with herbivory. Maybe it's a taste the plant has. Maybe it's really strong, like peppermint. Maybe it's nicotine, which is an insecticide. Maybe it's spines or thorns or something like that to keep animals away. Anybody know what kind of big cat this is? It is a jaguar. How'd you know?
Because of the.
Spots.
Space.
Spots. That explanation would also suffice for the cheetah, the leopard.
His face.
How the spots are
It's like I see it on cars all the time.
designed.
His face apart
Yeah,
from.
like this one here, you have a spot inside a spot. Rosettes is what they call them.
A spotted spot.
Spotted spot. Spotted spot.
Yeah,
Yes,
swag.
that's a jaguar.
Aren't jaguars also like thicker?
They are bigger after lions, tigers and lions. I think they're the third biggest big cat.
Yeah, because cheetahs are usually more slender for running.
Exactly. And leopards are smaller too.
Mhm.
Biogenic chemical cycles. Now, I'm going to mention these, say where they're most effective, where they most impact ecosystems, but that's about it. I don't want to get into any detail with this. Nutrient cycles involving both biotic and abiotic components. You've got carbon, which is global, water, which is global. Carbon dioxide ends up in the atmosphere. We talked about global warming or global climate change. But it gets up there and it impacts everything over the entire planet. Water, the same way. The water that evaporates from the ocean eventually works its way all the way across the U.S. Nitrogen, phosphorus, these are more local. These are things you use as fertilizers to put around your plants to help them grow. Might eventually get washed into a given area, like a pond or a lake, causing eutrophication. All this sounding a little familiar, hopefully, short term. Now, we talk about these, but there are natural processes that occur all the time, putting carbon, water, nitrogen, and phosphorus back into the environment that we don't need, or the environment doesn't need us to be doing all this stuff. They could get on very nicely without us. So there's enough natural sources of all these things that would enable the environment to survive without us. Carbon dioxide, we talked about that. Even though things like plants take carbon dioxide out of the atmosphere, remember they also respire, so with respiration, they put it back in. The water cycle gets over the ocean, moves over the land. Things like mountain ranges will cause clouds to drop their moisture before moving on, but it'll just pick up more moisture as it goes along. Nitrogen, we've got a ton of nitrogen in the atmosphere, but very few organisms can use it directly from the atmosphere. Oftentimes what happens is you need to convert that nitrogen into a form organisms can use. We get it from our diet. Other organisms like plants have bacteria living in their roots that will take that nitrogen from the atmosphere and convert it to a form they use. Phosphorus, a lot of it is in rocks. The rocks weather, it pushes phosphorus out into the environment where it can be absorbed by plants. Eventually, as the plants die, it rains, the phosphorus ends up back in the water, back in the sedimentation, through geological processes, and it's back up in the rocks and starts all over. Tridivore again. I think this is kind of redundant. I could have taken this one out good. Organism that feeds on dead or decaying organic material, detritus, also known as decomposers. Rate of nutrient cycling is dependent upon the rate of decomposition. Warmer temperatures plus more moisture equals faster rate of decomposition. I know why I did it to get to this one. Okay, so yeah, a little redundant. Learn it once, know it twice. So we've got things like fungi, prokaryotes, protists out there who are breaking down dead or decaying organic material. There's a lot of carbon, phosphorus, nitrogen, all kinds of elements that the environment needs trapped inside of living organisms. And then once they die, decomposers are able to liberate that and return it back to the environment. And again, warmer temperatures and more moisture equals faster rate of decomposition. So how quickly decomposition occurs, how warm it is, and how much moisture there is, determines how quickly those nutrients are going to be returned back to the environment. Tropical rainforest, 10% of the nutrients are contained within the soil. It's funny because everybody thinks tropical rainforests must be so nutrient rich where the soil is concerned. They cut them down, they try and graze cattle there, they try and grow crops there, and they might have enough nutrients for a season or two, but after that, everything pretty much reverts to nothing. So what people don't realize is most of the nutrients are living organisms around tropical rainforests. We have fast nutrient cycling here. As soon as something dies, it's very quickly broken down and returned back to the living organisms because of the higher temperature and moisture. In a temperate forest, 50% of the nutrients are contained within the soil. Slower nutrient cycling, lower temperature, moisture. So the nutrients spend more time in the soil because the processes don't occur as quickly because you don't have as much warmth or as much water. And so they will occur more gradually. So that means they spend more time in the soil, making the soil more nutrient rich. Okay, don't write down the first part, just where it picks up 1, 2, 3. Human activity disrupts nutrient cycles by removing nutrients from one place and adding them to another. Novel materials which are added, things like fertilizers, pesticides, things like that, in some cases are toxic. Nitrogen is the main nutrient lost in agriculture. Synthetic fertilizers increase nitrogen in the soil. Legumes increase nitrogen in the soil. Okay, I'm not going to put a picture of fertilizer up here. I think you guys can figure out what fertilizer is. A lot of fertilizers are ammonia-based because that's a form of nitrogen plants can take up. It's also what they use for making bombs because it is nuclear stuff, potentially explosive. Legumes are plants that have the nitrogen-fixing bacteria living in their roots. And they live in these tiny little nodules on the roots. And what they do is they take nitrogen out of the atmosphere, convert it into a form that plants can use, and in exchange, since they're already in the roots, plants say, yeah, sure, go ahead. I'll just dump any and all food that you want. You do me a favor, so I'll do you a favor. Picture on the right, all these little nodules. The plant looks like these bacteria living in the root systems. So a case of mutualism. The bacteria provide the plants with all the nitrogen they can use. And in exchange, the bacteria get a nice place to live and all the food they could possibly use.
So that's a mutualistic relationship.
I guess they both benefit.
And what is that the same as symbiotic? Or?
Symbiosis is just two organisms living together. Mutualism is a specific type of symbiosis. Oftentimes it's used as mutualism, but it's not. Critical load. Amount of nutrients added, nitrogen and phosphorus that can be absorbed by plants without damaging ecosystem integrity. You have to get just the right amount of fertilizer on those plants for the plants to absorb without putting too much down. If you put too much down, it rains, it's going to wash that fertilizer off to somewhere, and it will probably have disastrous effects, especially if you use too much. So critical load, amount of nutrients added, specifically nitrogen and phosphorus that can be absorbed by plants without damaging ecosystem integrity. So critical load, that's right up to the point where you can add it and the plants can use it. Sorry. anything above the critical load, when you exceed that, then you start harming the environment. What happens? Excess nutrients leach into groundwater or run off into aquatic ecosystems. Now, we talked about eutrophication. This is what happens. These are the effects of it. Contaminates water supplies, chokes waterways. You get too many plants out there, and it will actually lead to things like fish kills. Kills fish. They are struggling for oxygen. I don't know if that's really what's happening there. I mean, obviously they're struggling for oxygen. I just found the picture. I kind of liked it. Kind of illustrated what happens before they die. See that are pictures of dead fish. I think it's a little bit better. So contaminates water supplies, chokes waterways, leading to eutrophication, and kills fish. Sources of contamination, we've already talked about fertilizer runoff, agricultural, for agricultural and landscaping, sewage, industrial waste as well, especially if it has a high phosphate content. I don't know if you noticed, maybe you don't do your own laundry, maybe your mom still does it for you. I don't know. But you can actually buy detergents that are phosphate free. Because phosphates are often found in soaps, and it can also lead to eutrophication and animal waste runoff. Let's say you've got a large herd of cattle. If you've ever driven by any place that has large herds of cattle, temporarily or permanently, this does not smell nice. It's all that animal waste. It runs off, okay? It rains, it washes it down into the lowest point, particularly where you find water wells. And then you get the same process there, just that you would fertilizers. They just keep building up and building up, causing the plants to continue to grow. You get algae, and it wipes everything out. Results of contamination, algal blooms. This is where you have excessive growth of algae. What happens, you get oxygen saturation during photosynthesis during the day when the plants are carrying out photosynthesis, but the plants just don't go to sleep at night. What they do is they convert to cellular respiration. So all that oxygen they put in the water, now they're taking it back so they can carry out cellular respiration. So you get oxygen depletion during the night, during respiration. So we talked about eutrophication earlier. I know it seems repetitive, but actually we're talking about now what happens more specifically as a result of this. Introducing the before, now we're dealing with the effects. And of course, there's other ways you can disrupt the environment. That's precipitation, often known as acid rain, but anytime we put these materials in the atmosphere, any form of fall, could be mist, could be fog, could be snow. Anything with a pH of less than 5.6 is considered acid precipitation. Burning wood, coal, or fossil fuels releases sulfur and nitrogen, which react with water, forming sulfuric and nitric acids. It lowers the pH of aquatic ecosystems. Obviously, you've got something acidic being added to water that's relatively neutral. It's going to turn the water acidic. Also alters soil chemistry of terrestrial ecosystems. I remember living in Tennessee, driving to the top of the Smoky Mountains, about 45 minutes from the University of Tennessee. And you get some of the higher elevations, and you see trees that are just dead up there because of the acid precipitation. It just wipes them out. They can't tolerate that much acid in the soil. So you see trees standing with no coniferous trees, so no needles on them or anything like that, just shells and trees. Anything marble is going to be eroded away by acid precipitation. I mean, there's some places, marble, concrete, anything like that, whatever they use, in Rome, some of these older structures that's been around for thousands of years because of all the traffic over there and everything, it's leading to acid precipitation, destroying a lot of the structures over there.
What's that picture of?
I think it's it used to be a face, an angel or something like that on a tombstone. Yeah, looks scary now. If you were rinsed off with acid precipitation, you'd be upset about it too. So here's what happens. Through whatever processes of burning wood, coal, or other fossil fuels, it puts sulfur dioxide, nitrogen oxides into the atmosphere. They mix with water and they come back down to the earth in this form of acid precipitation. It destroys plant life, pollutes rivers, streams, erodes the stonework like I've already shown you. Environmental toxins.
Russell,
Yeah.
where does that happen at? Acid rain?
Anywhere where there's a lot of industry going on. Maybe not as prevalent in some areas, it just depends. Like I said, Rome's one place that are really getting hit hard by it.
Mhm.
Where else you hear about it? Like I said, in the higher elevations, the Smoky Mountains just getting hit by it.
Okay.
It's pretty much global.
Wow.
To what degree it changes depending upon how much pollution there is in the atmosphere.
It's just because like we never really hear about it like that
I
much.
don't think China would have pretty extensive acid precipitation because of all the pollution they have.
Okay, because you think the weatherman would be like, oh yeah, today's acid rain, yeah.
It's rain today.
Yeah.
Bundle up. Okay, bioaccumulation and biomagnification. Two very similar sounding terms, increasing concentrations of potentially toxic substances in living organisms and in food chains. Okay, I'll quit. So increasing concentrations of potentially toxic substances in living organisms. That's bioaccumulation. One organism eats something, it gets into that organism. It accumulates in the body of an organism. Easily ingested but not biodegradable. It gets into the tissues and you can't get it out. It doesn't break down, it can't be removed. Okay, why the bald eagle? Because in the 1960s, the population of bald eagles almost crashed. They almost went extinct. And it had everything to do with bioaccumulation of environmental toxins, specifically DDT, chlorodiethyl trichloroethane. You don't need to remember that. I just like to impress you that I still know. DDT was an insecticide that was sprayed pretty much everywhere. I mean, not just around places where eagles lived, but in airplanes, on military bases, at beaches, anywhere where you might have, especially things like mosquitoes and stuff like that, pests for crops and everything, they spray DDT everywhere. It didn't seem to be as toxic or as harmful as former pesticides. But what we found that it was doing In the eagles, it was preventing them from laying hard-shelled eggs because the females could not deposit calcium into the eggshell. And so that led to soft-shelled eggs. The babies were born, they hatched, usually prematurely, and they wouldn't be ready and they died. And so you're starting to lose an entire generation of eagles coming along. But then we also found that it started causing cancer. We see cancer in eagles. And people started thinking, wait a second, if it's causing cancer in these birds, what's it doing to us? And so we don't use DDT anymore. So increasing concentration of potentially toxic substances in living organisms is bioaccumulation. Biomagnification is the same thing but in food chains. Exponentially increasing at each level. Well, eagles eat fish. Fish swim in water. Let's say Farmer Brown sprays his crops with DDT and it rains and it washes everything down in a local creek, which pushes it into the stream and eventually out into the lake. There's fish in the lake. Doesn't affect them at first, it's not directly. It gets into the food chain. Maybe it starts being incorporated into the algae. Maybe you've got tiny microorganisms that are eating the algae, so they incorporate the DDT. You've got small fish eating the microorganisms, so they get the DDT. And then you've got bigger fish eating the smaller fish, so they get the DDT. And eventually, the fish-eating birds like the eagle top the food chain getting the most DDT. Because if you're one little microorganism, you're not just eating one piece of algae, you're eating lots of it. So every time you eat algae, you build up more and more DDT. It doesn't leave, it stays. Biodegradable. Small fish, you don't eat just one little microorganism, you eat lots of them. So you get more DDT in small fish. Because everything the microorganisms picked up, now the small fish have, and then some. The bigger fish, same story. More DDT. Just building up as it goes through the food chain, you get the eagles to the top of the food chain, and they're getting the highest concentration of DDT. And so this is where it was impacting the environment the most. Plus it's our national symbol. Looking pretty bad at our national symbol, almost 26. The first generation pesticides were not great things. Some of you've had chemistry before, arsenic, lead, mercury. These were the heavy metals. Yeah, it kills stuff. So if you spray this on plants, you're going to kill insects, but you're going to kill everything else in the area too. It was expensive to produce, persisted in the environment, lasted, could not get rid of it. Toxic to all living organisms, including humans. However, insects over time developed resistance. You could spray something on insects to try and kill them and wipe out 99% of the population. And you might be thinking you've done pretty good. Well, in about 5 years, that 1% of the population that survived is now going to come back resistant to whatever you sprayed everything else with, and it's going to be back in full force, like I said, within 5 years. So it wasn't working great. So heavy metals, arsenic, lead, and mercury. And you hear about this stuff. Every now and then you hear about somebody who was killed by arsenic poison. Lead, we took lead out of our paint, gaslights, because of the damage it did to the environment. Sometimes we still have lead in paint, and they always warn you, don't paint nurseries with leaded paint, because for some reason, little kids like to peel paint off the wall and eat it. I don't know why. And it's a toxin. It causes denaturation. It starts breaking down the proteins. And so if you're a little kid and you're starting to develop and everything, all those proteins are going to get broken down. Could lead to things like health problems, mental retardation, and death. And then mercury. You know the dangers of mercury. You hear about it all the time. You buy byproducts that don't have mercury in them. Expensive, lasts for a long time, kills everything, and then the thing you were trying to kill the most develops resistance to it. So that's the drawing board. Then you come out with synthetic organics like DDT. They were inexpensive to produce. Well, there's one good thing. They persisted in the environment. Well, that's still not the greatest thing, but they only kill insects. Okay, that's great. And they covered a broad spectrum. Instead of spraying 2 or 3 different types of insecticides, you could spray one, and it wiped out all the insects. This is out of Life magazine back in 1948. Here is somebody drinking a soda, eating a sandwich, and they're spraying DDT all around her to show her that it's not going to hurt you. Google it sometime, you'll see where there are beaches, spraying the beaches and kids running in the mist of the DDT. I mean, it was widely used everywhere by everybody. And nobody knew anything bad was going on with it until we started looking at the birds, yes.
What was the ultimate like goal of DDT? Like
Insecticide.
to wipe out all bugs?
Not all bugs, just the most prevalent ones like mosquitoes and any kind of insects that farmers might be having trouble with their crops.
Just wipe them out totally? Like totally just
Broad spectrum,
level them all together?
toxic only to insects too.
Wouldn't that affect the ecosystem altogether too?
You're not worried about that.
Okay.
You're looking at resort communities like beaches and lakes and things like that. So obviously you're not looking at preserving the environment there. You're looking at agriculture that goes against most ecosystems. Yes.
So then how do they do it with organic food when they say, oh, no pesticides and everything? Wouldn't there be like animals or little insects growing in your crops no matter what, so they just don't?
There could be. I mean, I keep hearing all this talk about how much is valid. You know, you really have to be careful as to what you get if you're vegetarian because there could be some insects in the mix. Just because they end up in the grain, they end up in the peanuts, there could be insects in your peanut butter, all this stuff.
Mhm.
So, yeah, it could be. Okay, here's how it works. DDT ends up in the water, gets into the microorganisms, the small fish, the bigger fish, and eventually at the top of the food chain. And you see in the water, 0.0003 parts per billion, 0.04 parts per billion, 0.5 parts per billion, increasing exponentially, 2 parts per billion in the fish, and then the eagles get the most, we're up to parts per million here, million, 25 parts per million. And so, top of the food chain, they were getting the most DDT. Like I said, DDT accumulated in the tissues of eagles, interfering with the deposition of calcium in eggshells. During incubation, eggshells would break, resulting in a significant decline in reproductive rates. Well, that kind of makes sense. So here we are in 1963. We had 487 nesting pairs of bald eagles, so a little over 1,000 total, maybe 1,500, 2,000 max. Okay. In 1973, DDT was banned. We already start to see an increase. And then we go all the way to 2006. Yeah, they've rebounded pretty nicely. In fact, they're no longer in danger. They're considered threatened. In 1963, there were 487 nesting pairs of bald eagles in the lower 48 states. Their decline directly linked to DDT. Since 1972, the use of DDT was banned in the U.S. But guess what? We still make it. We still produce DDT and ship it to countries where they don't have a strict environmental regulation. Central South America, they still use it down there. We know this because we still see birds migrating south for the winter and coming back and laying soft-shelled eggs, so they're getting it down there. In 1973, the bald eagle was placed on the first list of the Endangered Species Act. It was an act passed, revolutionary, especially for the U.S., but never passed today, saying, okay, these animals are protected by the government, that you can't hunt them, you can't kill them for any reason, you can't do anything in the areas where they might be living, breeding, you have to leave them alone. In 1990, there were 4,000 nesting pairs in the lower 48, so it rebounded by 10 times. And 2003, the bald eagle was downgraded to threatened. It might even be removed from threatened, I can't remember. Atmospheric carbon dioxide. Carbon dioxide concentration has been increasing since the Industrial Revolution due to combustion of fossil fuels and burning of enormous quantities of wood, as well as deforestation. Okay. Industrial Revolution started a little bit before 1850. Up until then, we were an agricultural society. Everybody lived on farms. You pretty much ate what you grew, had a little bit left over, you sold it, and made a living. Not a great living, unless you had like a huge farm or a huge ranch, and you employ lots of people to grow lots of stuff. Then you might be among the wealthy. Well, people wanted a better life. And with the advent of factories, people started moving back into the city, working in factories. The work was steady, so was the pay. So with more and more factories, they were burning things like coal and oil and wood. But there weren't the environmental concerns back then, so pretty much everything went up the smokestack and out into the environment, including carbon dioxide. So in 1850, 274 parts per million of carbon dioxide. Today, 385 parts per million. So we've increased it considerably. Now, keep in mind, this is about the 1960s. Most countries have a lot of environmental controls in play trying to clean up what comes out of these smokestacks or chimneys of these factories. And so if we weren't cleaning that up like we are now, that would be even higher. It's just there's a lot more people now than there were back in 1850. So more people, more factories. And deforestation, kind of like a two-edged sword here. Sometimes you need the wood to burn in the factories. You may not use it all. You're cutting down the trees to take the carbon dioxide out of the atmosphere. And then if you don't need them, you turn around and you burn them just to get rid of them. And so you're putting the carbon dioxide right back into the atmosphere. So it's a lose-lose situation. And this leads to the greenhouse effect. Now, initially, Earth was kind of inhospitable, not very good for life. And it wasn't until something like the greenhouse effect initially took place that it started to warm the planet up and make it a little more habitable, a little bit nicer place to live. Carbon dioxide, water vapor, other gases intercept much of the reflected solar radiation from Earth's surface, re-reflecting some of it back to Earth. It's not a typo, re-reflecting. I like the word choice. So the sun comes down with its solar radiation, hits the planet, goes back up, and the atmosphere traps some of that. Now, some of it will go back into space, but others will be turned back to Earth to keep warming the Earth up. Now, initially, the greenhouse effect was a good thing. Think about like going to bed at night and throwing a sheet or a blanket on you just to keep you a little bit warm. Sleep throughout the night, no problem. Let's say for some reason you go to bed at night, you're a little bit more chilly, you throw a comforter on. You wake up in the middle of the night because you're hot, you're sweaty, and you take the comforter off. Well, that's where we are today with the greenhouse effect. At first, we just had a sheet or a blanket on us. Now we've got a comforter over the Earth. And we just can't kick it off that easily when we get hot. So we're dealing with the effects of that. Now, are we entirely responsible for the greenhouse effect, for global warming, for climate change? I think we'd like to think so. Because we're humans, and we have this superiority complex because we like to feel like we have dominion over everything on the planet, and we have total control of our destiny. It's not the way it works. Chances are we're going through a shift in the climate that would have happened with or without us. Are we contributing to it? Maybe a little. We could be making it worse. And of course that leads to global warming. Increase in average temperature of Earth's near surface air and oceans. Results from global warming, shifting precipitation patterns. I don't know if you've looked outside recently, but California's in a bit of a drought. That could have something to do with it. Got a lot more winds, a lot more sand blowing around. There's not a lot of vegetation growing in times of drought, so the sand's more loose and it picks up and gets blown around more. Check out the dust boils. Melting polar ice caps, rising sea levels, coastal flooding, mass extinctions. Now this is like worst case scenario stuff. Things they like to put into movies, things they like to talk about to sell papers or whatever, just to cause you to be a little bit afraid. Okay, can anybody name that animal? It's cute. It's a pika, P-I-K-A. And you find it in Central South America. Likes cooler environments, lives higher elevations. If it gets warm, it just climbs higher up the mountain. What if it keeps getting warm? Eventually it's going to run out of the mountain. And so something like this could be counted in that mass extinctions. Let's say our seasons get a little bit off. Feels like we went pretty much straight from winter into summer this year. Didn't have much of a spring. Well, let's say that caused things to bloom early. And let's say you're a bird and you've timed your migrations for generations, for year after year after year, to coincide with coming back when the plant blooms and insects are there to feed on the seeds produced, and you feed on the insects. Well, the plant bloomed early, the insects ate early, they've laid their eggs and died, and you get back and there's nothing for you to eat, what's going to happen to you?
You're gonna die.
So we talk about little things. We're not talking about mass extinctions like the Earth heating up too much, killing off coral reefs and things like that. That stuff could happen, but sometimes it's in much more subtle ways. Little ways, things like that could happen with just minor shifts. Depletion of the atmospheric ozone. The ozone layer is about 70 to 25 kilometers high in the Earth's atmosphere, containing high concentrations of ozone. blocking 97 to 99% of solar ultraviolet radiation. Okay, it's a good thing having it up there. It's a very good thing having it up there, not down here, because guess what? Ozone is toxic. If you breathe in ozone, it will kill you. Okay, I know it's oxygen, kind of crazy. You think I need oxygen to live, but not that much. Not O3, just O2. So it's in this layer above the Earth. And what it does is all this UV radiation that bombards the Earth every day, most of it is filtered out by the ozone layer. Now, where is ozone thinning?
Where's it what?
Thinning.
Isn't it over the whole?
City?
Okay, one pole more than the other. Go ahead, Sam. You could have said South Pole. I would have accepted that. Antarctica, South Pole. And sometimes the year that extends up a little bit. Well, what countries might get hit by that? Now you're doing geography, so all of you earlier now geography. Australia would be one. What else?
South America.
South America. That's not really a country, it's a continent, but I'll accept it. And what else?
South Africa.
South Africa. Yeah, that is a country. So yeah, those areas closest to the pole are going to be affected most when this expands. If I heard recently about Hugh Jackman having skin cancer removed, kind of makes you wonder how much it had to do with him being Australian. So you get entertainment now too. Man, you just get it all. So much more for your money. Most apparent over Antarctica. Here it was in 1979. Here it is more recently, 2006. Obviously, you can see more of Antarctica here, so there's a bigger thinning in it. The thinning's at 75 due to CFCs, chlorofluorocarbons. I've got a spray can there because that's where you used to find them. It's a propellant that you used to put in spray cans, so when women would put hairspray all over their hair, anything pretty much that we sprayed had this in it. Well, what happens is, we'll talk more about this in a little bit, how it happens in the next chapter. It gets up to the atmosphere, and it doesn't react very well with ozone. It tends to break it down. Now, along came the Montreal Protocol in 1989. This was phenomenal, because what happened was, pretty much the entire world got together and said, okay, this is a bad thing, we need to stop doing this. And so they pretty much banned, or at least extremely limited, those things which were thinning out the ozone. CFC is gone. The thing they're having a lot of trouble with is trying to regulate Freon, which also contributes to the thinning ozone layer. Where do we use Freon? Air conditioners in your car, in your home, all this stuff. Okay? Especially living out here in the desert, we couldn't live without air conditioning. I mean, just be miserable. But they keep reformulating, trying to come out with stuff that's better, less destructive of the ozone. So, consequences of ozone layer depletion. Increases in cases of skin cancer, cataracts, because it affects your eyes as well. Adverse effects on the ecosystem. Some crops, some plants can deal with a lot of sunlight, some can't. And it could very adversely affect them. So that's what happens. Okay, this is a picture of Australian school kids. What do you notice about them all?
Hats.
They're wearing hats. Yeah, they recommend when you go out in Australia, when you hear about the UV ratings that we have in the desert, when you go out today, wear a hat, wear glasses, wear long sleeves, long pants, plenty of sunscreen. This is even worse down there. Okay? So it gets to be much, much worse. So they're required to wear hats anytime they go outside, whether it's school. Okay, we've got one chapter left. That chapter is not going to be on the quiz on Thursday. It's enough to email you that specifically said that. I should be able to get through that chapter. It's about this long, actually 2 slides shorter, after the quiz on Thursday. So we'll do that, and then that's it. And you don't have your final until a week from Thursday. You do have the lab exams this Friday. Don't forget about those. Be studying, preparing for that, make sure all your work and your lab manuals are finished. Any questions about anything? I could start into the next chapter, but I really don't feel